Good morning, everyone. This is an audio recording for the visually impaired student from the book Pradeep Inorganic Chemistry, Volume 2 by Dr. K. Basin. Chemistry of lanthanoids element. Lanthanoids are the element present in period 6 of the periodic table with atomic number 57 to 71. Since the last electron in the atom of this element enter the 4f orbital, therefore these elements constitute what is known as f block element. These elements are also named as inner transition element. This is because these elements constitute a transition series within the third transition series. More precisely, the 5D transition series. These elements are located in first row of the two rows of elements kept at the base of the periodic table. The first element of the series is named lanthanum. Z is equal to 57, and in a group of 14 elements following lanthanum which involve the gradual filling of 4f orbital is called the lanthanoid. In other words, elements starting from cerium Z is equal to 58 and ending with lutetium Z is equal to 71 are known as lanthanoid. The name lanthanoids was wrongly coined as the ending "ide" more correctly means a negative ide. Such a oxide or chloride ion for a few years. IUPAC suggested a new name lanthanum instead of lanthanoid to that elements. However, it was also disapproved soon because the ending on is preferred for non-metal, whereas the lanthanoid are also typically metallic element. IUPAC has finally approved these elements to be named as lanthanoid with the ending oid. These elements in the earlier year were called the rare earth element because of their occurrence in very small amount. However, nowadays the term rare earth element is itself misleading because many of these elements have been found to be abundantly available. For example, cerium Z is equal to 58 is as abundantly available as copper. Huge deposits of this element have been located in USA, USSR, Scandia and India. Periodic structure and position of lanthanoid in the periodic table. As already discussed, lanthanoid involve the gradual filling of 4f orbital. The ground state electronic configuration of each lanthanoid is occupied by the outermost shell n is equal to 6 by the 2 6s electron. Since the energies of 6s, 5d and 4f are similar, the order of filling the 4f orbital may show some irregularities. It is found that lanthanum Z is equal to 57. The incoming electron enter the 5d subshell and therefore it has the following electronic configuration. Lanthanum Z is equal to 57. Electronic configuration of xenon 4f0 5d1 6s2. However, as we move onward after lanthanum, the energy of 4f subshell becomes distinctly lower than the 5d subshell. As a result, the next electron in the cerium enter the 4f subshell. The electronic configuration of cerium is represented as cerium Z is equal to 58, xenon 54, 4f2, 5d0, 6s2. The filling of 4f subshell constitute till 1 reaches ytterbium, which has the electronic configuration ytterbium Z is equal to 70, xenon 54, 4f14, 5d0, 6s2. The f block element may be defined as those elements in which the last electron enter the anti-penultimate energy level is Zn minus 2 subshell. Since both the 6s and 5f orbital have been completely filled, the next electron has no choice but to go to the 5d subshell. In lutetium Z is equal to 71, the electron enter the 5d orbital and the electronic configuration is lutetium Z is equal to 71, xenon 54, 4f14, 5d1, 6s2. It is important to note that the electronic configuration of the penultimate shell n is equal to 5 is invariably s2p6 except for the three element with lanthanum Z is equal to 57, gadolinium Z is equal to 64 and lutetium Z is equal to 71. It is equally important to note that the 4f orbitals are unoccupied in case of lanthanum Z is equal to 57. 4f orbitals are half filled in case of gadolinium Z is equal to 64 and 4f orbital are completely filled in lutetium Z is equal to 71. General characteristic of lanthanoid. The general electronic configuration of the lanthanoids may be represented as lanthanoid xenon 54 4f0 to 14 5d0 to 1 6s2. The ground state electronic configuration of the outer shell of lanthanoid atoms are given in table 4.1. Physical constants of lanthanoids. Some of the important physical constants for lanthanoids are given in table 4.2. Some of the important physical constants of lanthanoid are given in table 4.2. First one is the ionization energy. Lanthanoids have low ionization energy. The first and second ionization energy of the lanthanoid increases in general, but will show little variation with atomic number across the lanthanoid series. The trend is less clear for the first ionization energy than for the sum of the three ionization. It is clear from the figure 4.1 that deviation are observed only for europium, gadolinium and ytterbium and lutetium, which involve the half-filled and completely filled f orbital. The first ionization energy for the lanthanoid roughly correspond to 550 kJ per mole, whereas the second ionization energy corresponding to 1150 kJ per mole. These values are comparable to calcium, which has the first and second ionization energy values of the order 590 kJ per mole and 1150 kJ per mole respectively. Important physical constants of lanthanoids are in table 4.2. Melting and boiling point. The melting point of any substance reflects the force of attraction between the atoms, molecule or ion that compose the solid. An inspection of the table 4.2 reveals that lanthanoids possess high melting and boiling point. However, the melting and especially the boiling point of lanthanoid do not show any regular trend across the lanthanoid series. The properties of the lanthanoid series suggest that 3 valence electrons per atom are involved in the metallic bond. The 4f electrons are not involved in metallic bond as these are located on the individual atom. In figure 4.1 shows variation ionization energy E with atomic number for the lanthanoids. As are well shielded from each other, the most clear-cut anomaly in the lanthanoid are provided by europium and ytterbium, which behave much as would be expected of divalent atom, indicating less than 3 electron per atom involved in metallic bonding. These are also the two lanthanoid which most radially from divalent ion in their compound. In addition, these two ions have half-filled and completely filled 4f subshell respectively. This explains the low melting point in case of europium and ytterbium as compared to the values for the other lanthanoid element. Third, density. The density of the lanthanoid do not display a regular trend across the lanthanoid series. Both europium and ytterbium have unusually low densities. Heat of fusion and heat of vaporization. The amount of heat required to convert a substance from a solid and its melting point to a liquid is called the heat of fusion, whereas the amount of heat required to convert a substance from a liquid and its boiling point to a gas is called the heat of vaporization. In both the cases, the energy required is used to overcome the attractive forces. In case of lanthanoid, the heat of fusion and heat of vaporization do not show a regular trend across the lanthanoid series. Electronegativity value. Pauling defined electronegativity as the power of an atom in a molecule to attract electron toward itself. The lanthanoid show the lower Pauling electronegativity values between 1.0 to 1.15. These values are very close to those of alkali metal 0.7 to 1.0 and alkaline earth metal 0.9 to 1.5. Since the electronegativity value of the lanthanoids are almost same as that of S block element, it is anticipated that lanthanoid form ionic compound. Oxidation state. Oxidation state of +3 is shown by all these elements and in most cases is the most stable oxidation state. Some of the lanthanoid in addition to +3 shows +2 and +4 oxidation state as well. However, +2 and +4 oxidation state are always less stable than the +3 oxidation state. The reason for unusual oxidation state of +2 and +4 can be attributed to the extra stability associated with the F0, F7 half-filled and F14 completely filled electronic configurations. Example giving various oxidation state are given below. +3 oxidation state, lanthanum +3, gadolinium +3 and lutetium +3. Lanthanum Z is equal to 57, gadolinium Z is equal to 64 and lutetium Z is equal to 71 distinctly display +3 oxidation state. This is because after the loss of 3 outermost electrons, these elements acquire the stable configuration of empty, half-filled and completely filled 4f subshell as shown in figure 4. As shown in table 4.3. plus 4 oxidation state, cerium plus 4 and terbium plus 4. The most stable oxidation state of cerium is plus 4. This is because after the loss of 4 electrons, cerium acquires the outer electronic configuration as F0, D0, S0, which corresponding to that of the noble gas configuration. Cerium Z is equal to 58. Cerium plus 4 gives xenon 54, 4F0, 5D0, 6S0 is equal to xenon. Similarly, terbium Z is equal to 65 acquires the half-filled F7 subshell configuration. Terbium Z is equal to 65. Terbium plus 4, xenon 54, 4F7. Plus 2 oxidation state, europium and ytterbium. The most stable oxidation state of europium is plus 2. This is because after the loss of 2 electron, europium acquires the outer electronic configuration of half-filled F7 subshell configuration. Similarly, ytterbium Z is equal to 70 acquires the outer electronic configuration of empty filled F14 subshell configuration. Europium Z is equal to 63. Europium 2 positive gives xenon 54, 4F7, and ytterbium Z is equal to 70. Ytterbium 2 positive gives xenon 54, 4F14. The outer electronic configuration of various lanthanoids in different oxidation state are shown in table 4.3. There are instances where some of the lanthanoid display plus 2 and plus 4 oxidation state without acquiring either F0, F7 and F14 configuration. For example, samarium and thulium shows plus 2 oxidation state with F6 and F13 electron respectively, which are 1 electron short of the required half filled F7 or completely filled F14 configuration. Similarly, Plasmodium and neodymium shows plus 4 oxidation state with F1 and F2 electronic configuration. The existence of such oxidation state, which cannot be explained on the basis of F0, F7 and F14 configuration associated with extraordinary stability, might be explained on the basis of other factors such as kinetic and thermodynamic factor. Magnetic property. The magnetic property in chemical compounds determine the presence of paired or unpaired electron. If substances containing only spin-paired electrons are placed in the magnetic field, these are weakly repelled by the field. This phenomenon is called diamagnetism. On the other hand, substances containing one or more unpaired electrons, when placed in the magnetic field, are attracted by the magnetic field. This phenomenon is called paramagnetism. It is important to note that the attraction for each unpaired electron is many times stronger than the repulsion of all the spin-paired electrons in that atom. Most of the lanthanoid ions, with the exception of lanthanum plus 3, lutetium plus 3, cerium plus 4, ytterbium 2 plus ions, are paramagnetic. The paramagnetism in the lanthanoid arises because of the presence of unpaired electron in the 4f subshell. The ions lanthanum 3 plus, lutetium 3 plus, cerium plus 4 and ytterbium 2 positive are diamagnetic because they have no unpaired electron. The magnetic behavior of a substance is expressed in terms of magnetic moment. The larger the number of unpaired electrons, the higher is the magnetic moment. The magnetic moment arises from two types of motion of this electron. The spinning of an electron on its own axis generates a magnetic moment called spin magnetic moment. Orbital motion of the electron around the nucleus also produces magnetic moment called orbital magnetic moment. The magnetic behavior in case of lanthanoid arises due to the contribution of both spin magnetic moment as well as the orbital magnetic moment. This behavior of lanthanoid is in the contrast with the behavior of transition element of d block, where the magnetic moment corresponds exclusively to spin only values. In case of transition element, the d orbital are not well shielded from the environment and interact strongly with the ligand surrounding the metal ion. Because of the electric field of the ligand, the orbital motion of the electron is restricted, quenched, that causes the orbital movement to decrease considerably. In other words, the orbital movement of the electron in case of transition element can be neglected. On the other hand, in case of f block element, the 4f subshell are well shielded from the surrounding and do not interact with the surrounding ligand. As a result, the orbital motion of the 4f electron is not restricted or quenched. Thus, the magnetic moment of the lanthanoid ion arises due to both electron spin and orbital spin of the electron can be calculated from the expression mu is equal to under the root 4s s plus 1 plus l plus 1, where s is the total spin quantum number and l is the total orbital magnetic moment number. Table 4.4 Magnetic moment theoretical and experimental for M3 positive lanthanoid ion. The simple relationship work only for the lanthanoid lanthanum 3 positive. F0 gadolinium 3 plus, F7 and lutetium 3 plus, F14 both lanthanum 3 positive and lutetium 3 positive had no unpaired electron and consequently both have zero magnetic moment value. However, the magnetic properties of the lanthanoids are different from those of transition element. In the lanthanoid, the spin contribution S and the orbital contribution L couple together to give a new quantum number J. The new quantum number J can have two type of value. J is equal to L minus S when the orbital is less than half full. J is equal to L plus S when the orbital is more than half full. Therefore, the magnetic moment value for the lanthanoid in Bohr magneton Bm is given by mu is equal to G under the root J plus 1, where J is the land splitting factor for the electron and is given by G is equal to 1 plus J plus 1 plus S plus 1 minus L plus 1 divided by 2J plus 1, which is equal to 1 and half plus S plus 1 minus L into L plus 1 divided by 2J plus 1. The theoretical and experimental determined magnetic moment value of the tripositive lanthanoid ion are given in table 4.4. It is clear that the table 4.4 that there is an excellent agreement between the theoretical and experimental value when the magnetic moment are calculated on the basis of spin and orbital contribution together. All the tripositive lanthanoids ion excepting lanthanum 3 positive and lutetium 3 positive contain unpaired electron and are therefore paramagnetic. A plot of the magnetic value of tripositive lanthanoid ion reveals that the magnetic moment value increases first up to neodymium and then decreases up to samarium. It increases steadily again and reaches a maximum value for dysprosium dy3 positive ion and then start decreasing till it reaches zero value for lutetium ions, which is diamagnetic. It is important to remark that the high value of magnetic moment for terbium 3 positive and dysprosium 3 positive and holmium 3 positive clearly demonstrate the role of orbital contribution toward the magnetic moment of the latter lanthanoids. Figure 4.2 shows the magnetic moment of tripositive lanthanoid ion, lanthanum 3 positive. The spin only value together are shown in solid line and the experimental line are shown as dark line. A distinct feature of the curve is an unusual shape. The unusual shape of the curve arises between when the F subshell is less than half filled and the spin and orbital magnetic moment work in opposition is that J is equal to L minus S. But when the F subshell is more than half full, they work together is that J is equal to L plus S. Color and spectral properties. Lanthanoid in their experimental state are silvery white, while many lanthanoid ions are distinctly colored both in the solid state as well as in the aqueous solution. The color of the lanthanoid ion depends preliminarily on the number of unpaired F electron. The color of the lanthanoid ion remains same even on changing the counter anion. Thus, color of the lanthanoid ion is characteristic of the cation. It has been found that lanthanoid ion containing NF electron often have a similar color to that with N minus NF electron. The color of the lanthanoid ion can be grouped symmetrically about the trivalent gadolinium ion as shown in table 4.5. Table 4.5 shows color of lanthanoid lanthanum 3 positive ion. Lanthanum 3 positive ion having number of 4f electron 0, that is colorless, and lutetium 3 positive ion having 14 electron in 4f subshell and having no color is that it is colorless. The color of the lanthanoid ion is due preliminary to the absorption of light from the visible region of the spectrum that result in the electronic transition within the 4f level. This type of transition is called F to F transition. A unique feature of the spectra of tripositive lanthanoid ion is that the absorption band are sharp line like band in the ultraviolet, visible or near infrared region. This behavior is in contrast to the absorption band of DD type transition metal is that nickel to positive, cobalt to positive ion, which appear as broad absorption band. The band of lanthanoid ion are so sharp that they are used for characterizing lanthanoid. The reason for very sharp absorption band is that of 4f electron. 4f orbitals are located deep inside the atom, thus they are effectively shielded from environment factor such as the nature and number of ligands Nature and number of ligand which form the complexes and form vibration of the ligand. A typical lanthanoid ion spectrum of holmium is shown in figure 4.3. Thus, the color of the lanthanoid ion does not change with different ligand. In other words, the absorption band is that color show little dependence on the nature of the ligand. In figure 4.3, UV and visible spectrum of holmium 3 positive ion. It is important to note that this behavior is in contrast with the transition element where DD transition gives absorption band whose position changes from ligand to ligand and width of the peak is greatly broadened because of the vibration of the ligand. Vibration of the ligand changes the external field. However, the lanthanoid in the +2 and +4 oxidation state with the same number of electron isoelectronic ion and do not have the same color as absorbed in case of lanthanoid in the +3 oxidation state. Some of the typical isoelectronic lanthanoids in the +2 and +4 are shown in table 4.6. Table 4.6 color of lanthanum 4 positive, lanthanum 2 positive and their isoelectronic lanthanum 3 positive counterpart. Apart from F to F transition, sometimes the color of the lanthanoid ion can also be attributed to F to D transition. The F to F transition of lanthanoid ion have low intensity because these transitions are not allowed. However, F to D transition are allowed. As a result, they show very intense absorption band. For example, cerium 3 positive, terbium 3 positive show very intense absorption band transition due to F to D. F to D bands are broad in contrast to narrow F to F band. In addition to F to F and F to D transition, the color of some of the lanthanoids ion can be due to the charge transfer. This transfer of charge occur from the ligand to the metal. This is more probably if the metal is in high oxidation state or the ligand has a strong reducing property. Charge transfer usually produce intense color. For example, strong yellow color of cerium 4 positive solution arises due to the charge transfer rather than F to F transition. The blood red color of samarium 2 positive is also due to the charge transfer. Ionic radii and lanthanoid contraction. Covalent and ionic radii increases on moving down a group in the periodic table. This is due to the presence of additional shell between the successive period. On the other hand, on moving from left to right across a period, the covalent and ionic radii decreases. This is attributed to the increased effective nuclear charge as a consequence of which the outermost electron are attracted more and more. This result in the outermost electron being pulled more and more closer. We also know that the shielding effect of electron decreases in the order S2 S is greater than P, which is again greater than D and again greater than F. The atomic and ionic radii of lanthanoid are given in table 4.7. For table 4.7, the atomic and ionic radii of lanthanum 3 positive ion of lanthanoid. A careful inspection of table 4.7 reveals that as we move along the lanthanoid series from lanthanum to lutetium, there is a gradual decrease in the size of the atom and ions. With the increase in the atomic number, it has been observed that in case of tri-positive lanthanoid ion from cerium 3 positive Z is equal to 58 to lutetium 3 positive Z is equal to 71, the ionic radii decreases from 1.03 angstrom to 0.86 angstrom. This shows that the overall decrease of 0.17 angstrom occur in going from cerium 3 positive to lutetium 3 positive ion. This is indeed a very small decrease in comparison to element of other group and periods. The atomic radii of the elemental lanthanoid also decreases from 1.83 angstrom to lutetium 1.73. The total decrease of atomic radii from cerium to lutetium comes out to be 0.10 angstrom. This small steady decrease in the atomic or ionic radii of the lanthanoid element with increase in the atomic number is called the lanthanoid contraction. Causes of lanthanoid contraction. The shape of the orbital account for the relative atomic radii of the F block element. The lanthanoid involve the gradual filling of 4f orbital. The lobe of the F orbital occupy markedly different region of space and are therefore far apart from each other. Consequently, the F orbital repel one another very weakly. Secondly, electron density in F orbital is low near the nucleus. As a result of being away from the nucleus, 4f orbital are not very effective at shielding other electron from the nucleus. Thus, with the increase in the atomic number and the nuclear charge, the effective nuclear charge expanded by each 4f electron increases. This increase the inward pull of the 4f electron and result in the reduction of the size of the atom of the ion. The contraction of the size of the atoms or the ion by pulling the valence electron inward due to the high nuclear charge and the poor shielding effect of the f electron is in the main cause of what is called the lanthanoid contraction. Consequences of lanthanoid contraction. Some of the important consequences of lanthanoid contraction are given in table given below. First is a steady decrease in the size of the lanthanoid ion. As a result of lanthanoid contraction, there is a gradual or steady decrease in the size of the decrease in the ionic radii of lanthanoid. Second is the electronegativity. There is a slight increase in the electronegativity of the trivalent ion. Third is the electrode potential value E naught. There is a small but regular increase in the electrode potential value E naught for the purpose M3 positive plus 3 electron gives M. Values of the electrode potential redox of the system M3 positive plus 3 positive gives M are given below. Fourth, resemblance of second and third transition series. The atomic radii of the element of a second transition series period 5 are typically greater than those in the first transition series period 4. However, the radii of the third transition series element period 6 are about the same size as that of the second transition series. This is similarly in the atomic radii is due to the presence of F block nearly the beginning of period 6 as shown in table 4.8. There is a pronounced decrease in the atomic radii along the lanthanoid. When the d block resume at lutetium, the atomic radii has fallen from 2.24 angstrom for barium to 1.72 angstrom for lanthanum. As a result of this, the atom of all the following elements are smaller than expected. In brief, as a result of lanthanoid contraction, the chemistry of second and third transition series resemble each other more than the element of first and second transition series. 6 is difficulty in separation. Because of the very small change in the size of the lanthanoid ion in the lanthanoid series, their chemical properties are alike. This causes the separation of element a difficult task. 7th, high density. The lanthanoid contraction is responsible for the high density of the element of third transition series. A block of iridium, for example, contain as many atoms as a block of rhodium of the same volume, but each iridium atom is nearly twice as heavy as each radium atom. Therefore, the density of iridium is nearly twice that of rhodium. 8. Difference in basicity. The size of the lanthanoid ion decreases regularly with the increase in atomic number in the lanthanoid. The decrease in the size of the cation tends to increase the covalent character. According to Fazan's rule, as a result, the bonding of the smallest cation and the hydroxide ion becomes mostly covalent. In other words, the basic strength of the hydroxide decreases. This explains clearly that LaOH thrice lanthanum hydroxide is the strongest while lutetium hydroxide is the weakest base. Similar to hydroxide, there is also a decrease in the basic strength of oxide of lanthanoid with the increase in the atomic number. This decrease in the basic strength of oxide and hydroxide of lanthanoid with increasing atomic number is also reflected in several other related properties. For example, first is the hydrolysis of ion. Due to the decrease in the basic strength, there is a slight increase in the degree of hydrolysis in solution from lanthanum 3 positive to lutetium 3 positive. It means lanthanum 3 positive ion are less radially hydrolyzed than the lutetium 3 positive ion. Second is the solubility of the salt. Hydroxide of lanthanides precipitate with decreasing pH value from the nitrates of lanthanum 3 positive to lutetium 3 positive at 20 degrees Celsius. For example, lanthanum 3 positive precipitate at pH 6.83 whereas gadolinium 3 plus precipitate at pH 6.83 while lutetium 3 positive precipitate at pH 6.30. Third is the thermal decomposition of oxyacid. The stability of the trinitrates of lanthanoid decreases with the increase in atomic number. Thus, lanthanum nitride, which is more basic, decompose little, whereas lutetium nitrates decompose readily. Complex formation tendency of lanthanoid. Compared to the transition element lanthanoids ion lutetium-3 positive do not readily form complex. It is preliminary due to the larger size of the ions which result in the small charge to ionic radius ratio. Lanthanoids ion form complexes preferably with fluorides and oxygen donor ligand. These form complexes with beta diketones such as acetyl acetone, oximes, ethylene diamine, tetraacetic acid, EDTA, and hydroxycarboxylic acid such as citric acid, COOH, CH2, COH, COOH, CH2, COOH. Acetyl acetone complex of the tripositive lanthanoid ion is shown below in figure 4.5. The lanthanoid element of the are often 6 coordinated in complexes. However, higher coordination number are also known in some complexes. For example, 8 coordination is found in lanthanum AC thrice, H2O twice, where AC is the acetyl acetone, as well as in the anionic species YCF3COCH, COCF4 whole 4 negative. The high charge density on cerium 4 positive is expected to form stronger complexes than the tripositive, and cerium 4 positive has been found to form the dianionic complexes CeNO3 whole 6 2 negative in non-aqueous medium and 2O4. This is an interesting complex in which the coordination number of cerium is 12. Nitrates ion behaves as a bidentate ligand as shown in figure 4.6. Figure 4.5 shows acetylene acetone complex of tripositive lanthanoid ion. Organometallic compound. Lanthanoid ion being highly electropositive do not form complex with pi bonding ligand like CONO. The inability to form complexes is also due to the non-availability of F orbital for bonding. However, lanthanoids form two types of compound. First is the predominantly ionic cyclopentadienydes, and second is the sigma bonded alkyl or aryl. The cyclopentadienydes can be prepared by the reaction of anhydrous LnCl3 and NaC5H5 in a polar solvent like tetrahydrofuran THF in appropriate molar ratio. Using this methodology, it is possible to prepare cyclopentadiene compound of the type LnC5H5 whole thrice, LnC5H5 whole twice Cl, and LnC2H5 whole C2H5 Cl2 in polar solvent. These complexes are highly solvated and monomeric in nature. However, in non-polar solvent, the tris compound is that C5H5 whole thrice are insoluble, while the bis compound LnC5H5 whole twice Cl dimerize. The alkyl and aryl lanthanoids can be prepared by the metathetical reaction either in ethers or in the THF solution. LnCl3 plus 3R Li gives R3Ln plus 3LiCl. Figure 4.6 shows 12 coordinated structure of CeNO3 whole 6 to negative ion. LnCl3 plus 4RLi gives Li R4Ln plus 3LiCl, where R is alkyl or phenyl. The triphenyl lanthanoids are polymeric compound. The first fully characterized compound was LiTHF whole 4 lutetium C6H3 Me twice Me2 whole 4, in which the lutetium atoms is tetrahedrally coordinated to 4 sigma aryl group. The methyl derivative have recently been obtained. Occurrence of lanthanoid. Lanthanoids were originally named as rare earth or rare earth element because they were believed to be rare. However, the term rare earth is misleading as these are actually fairly common now. The word earth was used because most of these elements occur as oxide, which in early times meant earth, with the exception of promethium, which is radioactive. All the lanthanoid occur naturally. Recent studies have revealed that some of the lanthanoid, namely cerium, lanthanum, and neodymium, occur in fairly abundant quantities. It has been found that lanthanum with old atomic number are less abundant than the lanthanoids with even atomic number. Cerium has been found to be almost as abundant as copper. All the lanthanoids excepting cerium and promethium are more abundantly than iodine. The abundance of the lanthanoid element and the number of naturally occurring isotopes are given in table 4.5. 4.9 tables shows abundance of the lanthanoid in the earth crust by weight and weight of natural isotopes. A number of minerals containing lanthanoids are also known. Some of the important minerals are: first is the monazite. Monazite sand is the most important and widely spread mineral. It accounts for 78% of the mineral lanthanoids. It predominantly contains phosphate of the lighter lanthanoid with cerium, neodymium, presmodium, together with small amount of yttrium, and the heavier lanthanoids along with the thorium phosphate. Monazite has been found to occur in Brazil, USSR, USA, southern India, and Malaysia. Basnesite. Basnesite is a mixed fluorocarbonate with the formula MCO3F, where M is cerium 3 positive, lanthanum 3 positive, neodymium 3 positive, and plasmodium 3 positive. Bastenacite differ from monazite sand as it does not contain yttrium and has negligibly small amount of thorium in it. Large deposits of the mineral bastenacite are formed in Sweden and New Mexico. Third is cerite. The mineral cerite contains double silicate of cerium, lanthanum, presmodium, neodymium, and samarium along with aluminium and iron. Extraction of lanthanoid from monazite. The mineral is crushed to obtain fine powder. It is digested with concentrated sulfuric acid till a paste of lanthanoid sulfate is obtained. The paste is separated by centrifugation and treated with cold water. When silica, being insoluble, is separated out, the solution containing soluble sulfate is neutralized with ammonia hydroxide. When thorium, zirconium, and titanium are precipitated as a respective phosphate, the resulting filtrate is treated with sodium sulfate. This treatment separate the lanthanoid elements into two groups. The lighter lanthanoids, lanthanum to samarium, are precipitated out as double sulfate, while the heavier element, gadolinium to lutetium, remains in solution as simple sulfate. The precipitated double sulfate of heavier element are treated with concentrated solution of sodium hydroxide, whereas these are converted into the mixture of the corresponding oxide and hydroxide. The mixture is subjected to washing to remove sodium sulfate from during the course of the process and allow to dry it in air at 100 degrees Celsius. During this work up, cerium gets completely oxidized to cerium plus 4 oxide cerium O2, whereas the other lanthanoids are converted to the ciscoidine Ln2O3. The resulting mixture of these oxides is treated with the dilute nitric acid HNO3. All the oxide except CEO2 dissolve to form the corresponding nitrates. CEO2 being insoluble in dilute HNO3, this crude sample of CEO2 is dissolved in concentrate HNO3. Addition of dilute sulfuric acid precipitate out cerium as basic nitrates of the formula CeOH NO3 thrice 3H2O, which is a red crystalline solid. The various steps involved in the separation of cerium are outlined symmetrically in the flow sheet diagram in figure 4.7. After the successful separation of cerium, the other lanthanoids are separated into individual elements by employing different method based preliminary on the principle of varying solubility. Methods of separation into individual component. The properties of metal ion are governed by the size and charge of the ion. Since all lanthanoids ion are nearly of the same size and invariably carry plus 3 charge, they have almost similar properties. As a result, the separation of lanthanoid from one another is extremely difficult. A number of methods have recently been developed based on the repeated fraction crystallization, fractional precipitation, ion exchange method, etc. for the separation of lanthanoid. The conventional method of separation take advantage of the slight differences in basic property, solubility or stability. However, recently ion exchange method has been found to be the simplest. Some of the methods are discussed below. First is the precipitation. With a small amount of the precipitating agent, a substance with the lowest solubility is precipitated out. First, suppose hydroxyl ion OH negative are added to a solution containing a mixture of lanthanoid nitrates LnNO3 thrice the weakest base lutetium hydroxide, which has the lowest solubility product, is precipitated first, and the strongest base lanthanum hydroxide, which has the highest solubility product, is precipitated last. The process, when repeated several times, help in the complete separation of lanthanoids. Second is the fractional crystallization. Simple salt of lanthanoids such as nitrate, oxalate, sulfate, perchlorate, etc., together with double salt such as 2 LnNO3 twice dot 3 MgNO3 twice dot 24 H2O form well-defined crystal. The solubility of this salt decreases from lanthanum to lutetium. As a result, salt of the at the end of the series is that lutetium salt, which have low solubility, will crystallize out first. Similarly, salt at the start of the series, say lanthanum salt, while are the most soluble, will crystallize out in the end. The process requires repeated crystallization to get good separation. This is a laboratory method of separation and is not preferred these days. Uh, Figure 4.7 shows a flow chart diagram for extraction of lanthanoids. Solvent extraction. This method of separation is based on the fact that solubility of lanthanoid nitrate in aqueous and organic solvent like tributyl phosphate is different. In the solvent extraction process, a dilute aqueous nitric acid solution of the lanthanoid is extracted by means of a counterflowing solution of tributyl phosphate in kerosene. Thus, in the extraction from aqueous nitric acid solution by the tributyl phosphate (TBP), the equilibrium is established. Ln3 positive aqueous plus 3 NO3 negative aqueous plus 3 TBP organic gives Ln NO3 thrice TBP thrice organic. The extent of extraction increases with the decrease in the ionic radius. In other words, the cation of element with higher atomic numbers are extracted first. Using this method, a high degree of separation is achieved. Complex formation. Complexing agent like ethylene diamine tetraestic acid EDTA and well known to form complexes with the lanthanoid ion. The stability of these complexes increased with the decreased size of the lanthanoid ion. Thus, lutetium ion Lu3 positive complex of EDTA is the most stable of all the complexes of lanthanoid with EDTA. If some acid is added to the solution of this complex with EDTA, the least stable EDTA complex will dissociate and release the lanthanoid, and addition of oxalic acid will immediately precipitate out the free lanthanoid, and preferably at the end. At the left hand side of the series is that cerium 3 positive, promethium 3 positive, Na3 positive, which are weakly complexed with the EDTA. Oxalate of the lanthanoid are insoluble in water. However, addition of oxalate ion to the EDTA complexed lanthanoid ion will not precipitate the lanthanoid ion as they are already complexed with EDTA. Change in oxidation state. Most of the lanthanoid exhibit an oxidation state of +3 in its compound, whereas a few lanthanoid shows the oxidation state +2 and +4 in its compound. As a result, lanthanoid with +3 oxidation state have properties altogether different from lanthanoid with +2 and +4 oxidation state. The difference in the property in different oxidation state is extremely useful in the separation of lanthanoid. Cerium can be represented from the mixture of lanthanoid easily because it is the only lanthanoid which has +4 oxidation state in aqueous solution. This is thus if alkaline KMnO4 is added to the mixture of lanthanoid, it is only the cerium which will be oxidized to +4 oxidation state. On account of high charge, cerium +4 is the smallest and less basic than cerium 3 positive or any other lanthanoid in +3 oxidation state, and consequently is less soluble. It can be separated by precipitating it as cerium hydroxide by the addition of NaOH, leaving behind the other trivalent ion in the solution. Similarly, europium can be separated from the rest of the lanthanoid because europium is the only lanthanoid which is stable in +2 oxidation state. Addition of zinc amalgam, a strong reducing agent, to the mixture of lanthanoid ion only reduces europium 3 positive to europium 2 positive, leaving the other lanthanoid in the +3 oxidation state. If H2SO4 is added at this stage, europium 2 positive is only precipitated as europium sulfate, europium sulfate EuSO4, while the sulfate of all the other lanthanide ion remains in the solution as Ln2SO4 thrice. It is important to mention that samarium 2 positive, yttrium 2 positive can also be separated by reducing with a zinc amalgam. However, these get oxidized slowly by water, unlike europium. Ion exchange method. Ion exchange method is one of the most convenient and efficient method for the separation and purification of the lanthanide. In this method, a solution of the lanthanide ion is passed through a column of synthetic ion exchange resin which contain the functional group COH or SO3H lanthanoid, and when comes in contact with the resin containing the acidic functional group undergo proton change exchange as lanthanum 3 positive plus 3H resin gives Ln resin thrice plus 3H positive. In the process, the lanthanoid ion are bonded to the resin and the H positive ion produced as washed through the column. The bonding of the lanthanoid ion to the resin depend on the size of the lanthanoid ion. Since lanthanoid ion are present in aqueous solution, these are heavily hydrated. The smaller the lanthanoid ion, the most heavily hydrated it is. Thus, lutetium ion, lutetium 3 positive, which is the smallest in size, is the most heavily hydrated ion. It means that the size of the hydrated lutetium ion is maximum. It means that the smaller size hydrated lanthanoid ion binds strongly with the resin and large size lanthanoid ion binds loosely with the resin. The bonded metal ion are eluted, that is washed off the column by a complexing agent. The commonly used complexing agent is a buffered solution of citric acid, ammonium citrate at pH is equal to 8 during elution. The ammonium ion elutes the metal ion from the resin as Ln resin thrice plus 3NH4 positive gives 3NH4 resin plus Ln3 positive. The metal ion in turn then form a complex by combining with the citrate ion. Ln3 positive plus citrate 3 negative gives Ln citrate complex. As already discussed, hydrated lutetium ion, being the largest size ion, will bind less firmly to the resin. It therefore will be eluted first. On the other hand, hydrated lanthanum ion Li3 positive, being the smaller size hydrated ion, will bind strongly to the resin. Therefore, it will be eluted in the last of all. Using ion exchange method, it is possible to separate all the trivalent lanthanoid ion based on the strength of which these are bonded with the resin, which in turn depend on the size of the hydrated lanthanoids ion. In brief, the heavier lanthanoid element will be eluted or washed down the column first, following by the less heavier element and finally by the highest lanthanoid element. Elution curve of the lanthanoid element from an ion exchange resin column is shown in figure 4.8. In figure 4.8, elution curve of lanthanoid element are shown. In the x-axis, volume of eluted is taken, and in the y-axis, relative concentration is taken. Production of lanthanoid element. We have listed in the preceding session a number of methods for the separation of closely related lanthanoid. In this session, we shall illustrate method of the production of element. Some of the commonly used method for the production of lanthanoid metal are described. Electrolysis of fused chloride. A mixture of lanthanoid chloride LnCl3 is fused with NaCl or CaCl2 and electrolyzed in a graphite line steel cell which serve as a cathode and graphite rod at the end. This process is mainly used for lighter low melting cerium and for samarium and europium. Second is the reduction of anhydrous chloride with sodium. Lighter lanthanoids such as lanthanum, cerium and gadolinium are prepared by the reduction of the corresponding trichloride with elemental sodium at 1000 degrees Celsius. LnCl3 plus 3Na positive at 1000 degrees Celsius gives Ln plus 3 NaCl. Ln is the lanthanum and cerium gadolinium. Third is the reduction of anhydrous trifluoride with calcium or magnesium. Heavy lanthanides are produced by the reduction of anhydrous trifluoride with the elemental calcium. Anhydrous trifluorides are preferred because these are non-hygroscopic and less volatile than the trichlorides, and secondly the resulting CaF2 produced is stable. 2 LuF3 plus 3Na at 1000 degrees Celsius give Lu plus 3 CaF2. Compounds of lanthanides. All the lanthanoids are soft and silvery white metal. They are highly electropositive and are therefore very reactive. The heavier lanthanoids are less reactive than the lighter lanthanoid because they form a protective layer of oxide on their surface. Most of the lanthanoid form compound in the plus 3 oxidation state. However, some lanthanoid compound in the plus 2 and plus 4 oxidation state are also known. Let us first of all discuss the compound of lanthanoid in the plus 3 oxidation state. Compound in plus 3 oxidation state, lanthanoid oxide Ln2O3. All the lanthanum metal tarnish radially in air. These turn in oxygen forming the corresponding Ln2O3. The oxide can also be prepared conveniently either by heating the carbonate or by decomposing the corresponding nitrate. 4 Ln plus 3O2 gives 2 Ln2O3. Ln2CO3 thrice gives Ln2O3 plus 3CO2, and 4 Ln NO3 whole thrice gives 2 Ln2O3 plus 2NO2 plus 3O2. Lanthanoid oxide are known to absorb water and carbon dioxide from the air to form the hydroxide and the carbonate respectively. As a result, these are basic in nature. The basic character of the oxide decreases with the increase in the atomic number of the lanthanoid. This is due to the lanthanoid contraction, wherein the size of the lanthanoid decreases from lanthanum 3 positive to lutetium 3 positive. Li2O3 is strongly basic, whereas Lu2O3 is a very weak base. Lanthanoid hydroxide. The lanthanoids are reactive metal. These react slowly with the cold water but more rapidly on boiling with the liberation of hydrogen to form the corresponding hydroxide. 2 Ln plus 6 H2O gives 2 Ln OH thrice plus 3 H2. The hydroxide can also be prepared by adding dilute solution of sodium hydroxide to a solution containing Ln3 positive ion. Ln3 positive plus 3OH negative gives LnOH thrice. The hydroxide are precipitated in the form of gelatinous precipitate. These hydroxide are ionic and basic. Lanthanoid hydroxide are less basic than calcium hydroxide but more basic than aluminium hydroxide, which is amphoteric. The basic character decreases with the increase in the atomic number because along the series. Thus, lanthanum hydroxide is the most basic, whereas lutetium hydroxide is the least basic. Lanthanoid halide LnX3. Lanthanoid trifluorides are obtained by the reaction of HF or NEF while with the sodium containing the lanthanoid ion Ln3 positive. Ln3 positive plus 3F negative gives LnF3. Lanthanoid fluorides are important because of their insolubility. However, fluorides of heavier lanthanoids are slightly soluble in excess of HF due to complex formation. Anhydrous lanthanoid chlorides are prepared by heating the metal in an atmosphere of chlorine or by heating the oxide with phosgene carbonyl chloride. 2 Ln plus 3 Cl2 gives 2 Ln Cl3. Ln2O3 plus 3 CoCl2 gives 2 Ln Cl3 plus 3 CO2. Hydrated chloride can be conveniently prepared by heating the oxide with appropriate ammonium halide Ln2O3 plus 6 NH4Cl at 300 degrees Celsius gives 2 LnCl3 plus 6 NH3 plus 3 H2O. The chlorides are non-volatile, deliquescent solid. They are soluble in water and crystalline with 6 or 7 molecules of water of crystallization LnX3.XH2O, where X is 6 or 7. Hydrated chlorides can also be prepared by dissolving the oxides or carbonate in hydrochloric acid. Ln2O3 plus 6 HCl gives 2 LnCl3 plus 3 H2O. Ln2CO3 thrice plus 6 HCl gives 2 LnCl3 plus 3 H2O plus 3 CO2. The anhydrous lanthanoid trichlorides cannot be prepared by simply heating the hydrated lanthanoids trichlorides. In fact, on heating, the hydrated trichlorides are converted to oxychloride. LnCl3.6H2O on heating gives LnOCl plus 5H2O plus 2HCl. Anhydrous lanthanoid tribromides and triiodides are prepared by the direct combination of the element. 2Ln plus 3x2 gives 2Ln x3, where x is bromine and iodine. The tribromide and triiodides are more susceptible to hydrolysis and are generally contaminated with oxyhalide. Lanthanide nitrides. At high temperature, the lanthanoid react with nitrogen to give nitrides of the formula LNN. It gets hydrolyzed by water like Aln to give the corresponding hydroxide with the liberation of ammonia. Ln plus H2O gives LnOH thrice plus NH3. Oxosalt of lanthanoid. A larger number of oxosalt of lanthanoid are known. These include nitrate, carbonate, sulfate, oxalate, phosphate and perchlorates. These are generally prepared by dissolving the lanthanoid oxide, hydroxide or carbonate in the corresponding acid. For example, Ln2O3 plus 3HNO3 gives LnNO3 thrice plus 3H2O. Ln2CO3 thrice plus 3H2SO4 gives Ln2SO4 thrice plus 3H2O plus 3CO2. LnOH thrice plus 3HClO4 gives LnClO4 whole thrice plus 3H2O. The resulting solution are cooled when crystal of hydrated oxo salts are obtained. Double salt of lanthanoids. It is important to note that lanthanoid sulfate are known to form double salt with ammonium and alkali metal sulfate of the composition NH4 whole twice SO4 dot Ln2 SO4 whole thrice dot 8H2O. Na2SO4 dot Ln2 SO4 whole thrice dot 8H2O. The double salt in case of alum are generally associated with 24 water molecule of crystallization. However, the double salt of lanthanoid cannot afford to be associated with as many as 24 water molecule of crystallization. This is because the lanthanoid ion are too big to coordinate to 24 water molecules of crystallization octahedrally as in alum. Compound in +2 oxidation state. As in an inspection of the table 4.3 reveals that +2 oxidation state is shown by the lanthanoid, namely neodymium, samarium, europium, terbium, thulium and ytterbium. Europium and ytterbium display the +2 oxidation state by acquiring the stable F7 and F14 electronic configuration. The most stable divalent lanthanoid is europium 2 positive and its chemistry is well studied. Europium 2 compound EuCl2 can be prepared as a solid compound by reducing EuCl3 with gaseous hydrogen under pressure. 2 EuCl3 plus H2 gives 2 EuCl2 plus 2 HCl. Europium chloride plus 2 HCl. An aqueous europium 3 positive solution can be reduced by a variety of reducing agents such as Mg, magnesium, zinc amalgam of electrolytically to give europium 2 positive. The chemistry of europium 2 positive resembles the chemistry of calcium in many ways. For example, the instability of the sulfate and carbonate in water, the insolubility of the sulfate and carbonate in water, the insolubility of the chloride in concentrated HCl, the insolubility of the metal in liquid ammonia. The dihalides are also prepared more conveniently by the reduction of the trihalide and with lanthanoids metal itself. 2 Ln x3 plus Ln gives 3 Ln x2. SMI2 and ytterbium iodide have been prepared in quantitative yield by reacting the metal with 1,2-diiodoethane. In anhydrous THF at room temperature, it is a very clean reaction. Ln plus I CH2I gives LnI2 plus CH2 double bond CH2. The stable diiodide of samarium, europium and ytterbium can be prepared by the thermal decomposition of their triiodide as 2 Lni3 gives 2 Lni2 plus I2. Europium 2 positive halides are stable in water. All other trihalide react with water with the liberation of hydrogen. Lanthanoid compound in +4 oxidation state. An inspection of the table 4.3 reveals that only cerium, prismodium, neodymium, terbium and dysprosium show the +4 oxidation state among the lanthanoid. The only +4 oxidation state which is stable in solution and has a rich aqueous chemistry in cerium +4. It is very rare to find +4 ion in the solution Because the very high charge leading to extensive hydration, cerium plus 4 compound are extensively used as versatile oxidizing agent in quantitative analysis. Among the stable halide of lanthanide in plus 4 oxidation state, only the fluorides of cerium, prismodium and terbium are known. Cerium fluorides contain obtained as a white compound can be prepared by oxidizing CeF3 with element fluorine at room temperature. 2 CeF3 plus F2 gives 2 CeF4, whereas TbF4 can be prepared from TbF3 at under F2 at 300 degrees Celsius. The stable diiodide of samarium, europium and ytterbium can be prepared by the thermal decomposition of their iodide as 2Lni3 plus gives 2Lni2 plus I2 plasmodium plus for oxidation state fluoride FPrF4 can be prepared indirectly by fluorinating a mixture of NaF and PrF3 with elemental fluorine, which give Na2F PrF6. Extraction of NaF from Na2 PrF6 with liquid HF gives PrF4. Neodymium plus 4 fluorides is known only as a double salt CS3 and DF7, which is formed by the fluorination of mixture of CsCl3 and NdCl3. Some of the important reactions of the lanthanoids are summarized in the box. Summary for review. The lanthanoid are F block element. The chemical properties of all the lanthanoid elements are very much alike. The general electronic configuration of lanthanoid can be represented by Xe F 4F 0 to 14 5D 0 to 1 6s2. The most common oxidation state of all the lanthanoid is +3. The color of the lanthanoid ion arises due to absorption of light from the visible region of the spectrum. The absorption occurs due to F to F transition. The small steady decrease in the atomic or ionic size of lanthanoid element with increase in atomic number is called the lanthanoid contraction. Lanthanum hydroxide is more basic than lutetium hydroxide, whereas lutetium hydroxide is the least basic. Lanthanoid ion, because of their large size compared to transition element, have little tendency to form complexes, and lanthanoid do not form oxocation. Thank you.